Hello, today we're going to talk about the Higgs boson and the associated Higgs field. And the first thing to say is that these may not exist. They have not yet been found. They are the subject of the experiments at the Large Hadron Collider, but as of yet we do not know that they definitely exist. Before we get into the substance of the Higgs, we first need to understand what we mean by fields. Let's take a room. Inside that room will be a temperature. You could put a thermometer on the wall of the room and it would measure the temperature. But is that the same temperature everywhere in the room? Well, not necessarily. It might be a bit cooler by the windows or by the draft of a door. What you could do is to take this thermometer and measure the temperature at every single point in the room. And for every point in the room, you would have a separate temperature. And that list of numbers, which would represent the temperature at every point, is known as the temperature field. As it is, it just sits there and does nothing until something happens with which it can interact. For example, if you were to introduce an ice cube, then the ice cube would melt if the temperature of the room was significantly higher than the ice cube, and consequently you would get water instead of ice. In other words, the temperature of the room, the temperature of the air molecules, would cause the ice to melt in certain circumstances. But if there were no ice there, then the temperature field simply sits there. It's the same with an electric field. If we take two plates and we put a battery such that this plate is positively charged and this plate is negatively charged, we say that there is an electric field which runs between the plates. And there's a value for that field everywhere between those plates. It just sits there. But if you were to put an electron in that electric field, then the electron would accelerate towards the positively charged plate. In other words, when you put something in the field that interacts with the field, then it causes that electron to move. By contrast, if you were to put, say, a neutron, which is neutrally charged, a neutron will not interact with the electric field and will simply sit there. So the electric field has no effect. So the question is, what did Peter Higgs think he was doing when he created what is now known as the Higgs field and the Higgs boson back in 1964? Well, he was trying to answer the question, what causes elementary particles to have mass? And why do some have mass and some don't? We have already looked at elementary particles in other videos. They're set out in what is called the Standard Model. Here we have the Standard Model in a diagram form. There are 6 quarks, there are 6 leptons made up of 3 types of electrons and 3 types of neutrinos, and this line here is the 4 so-called gauge bosons. And those are what are called elementary particles. There is nothing that is known to be smaller than them. But if you look, you'll notice that the photon and the gluon have no mass at all. Whereas the other particles have varying masses, going from a neutrino, which is this neutrino here, is almost massless, an electron 0.5 of any MeV, an up quark 2 MeV, right the way up to a top quark, which is 171 GeV. 2 of the bosons are massless, but the Z boson has 90 GeV of mass. The W boson has 80 GeV of mass. And in case you're puzzled why we are describing mass in terms of energy, this just comes from the term that E equals mc squared. And what you do is you take the mass, which is very, very small indeed, multiply it by c squared to get a number which is strictly expressed in energy terms, but these numbers are rather easier to understand than something that might be, for example, 10 to the minus 27 kilograms. So why is it that some particles have no mass, and some particles have mass and different masses? That's what the Higgs is about to explain. I should just say, however, that the Higgs field does not explain why a proton has mass, or indeed why I have mass. Those are quite different things. The Higgs explains why elementary particles have mass. If you think of a proton, for example, that consists of 3 quarks, 2 up quarks and 1 down quark. And we just had a table that showed that up quarks have 2 MeV of mass and down quarks have about 4 MeV of mass. So the total mass of the quarks inside a proton is about 8 MeV. And yet the total mass of a proton is about 938 MeV. So how can a proton be that heavy when its constituent parts weigh only a fraction? And the answer is to do with what is called quark confinement. It's really based on the Heisenberg uncertainty principle. If you take 3 quarks and you constrain them to be inside a proton which is no bigger than 10 to the minus 15 meters, then they will have a huge amount of energy associated with that confinement, which by E equals mc squared is manifested in mass. So the proton gets its mass, and consequently I get my mass, from quark confinement. But what gives the quarks themselves mass? That's what the Higgs explains. Massless particles must travel at the speed of light. The reason for this is that when we did our videos on special relativity, we derived the formula that E equals gamma mc squared. Gamma is effectively the Lorentz transform. It's 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the observer. Now what this suggests is that when m is 0, the energy would be 0. And for a photon, for example, which is massless, you would expect all photons to have 0 energy. But we know that photons have energy. Einstein said that energy comes in packets consisting of the Planck's constant multiplied by the frequency of the wave of which the photon is a part. But how can a photon have an energy if its mass is 0? Because this formula would tend to suggest that energy is also 0. And the answer is that if and only if the particle is travelling at the speed of light, which means that v is also c, this term becomes 0, and 1 divided by 0 becomes infinity. And then the energy equals gamma, which is infinity, times mass, which is 0, times c squared. And that is mathematically undefined. Infinity times 0 is not defined, but it isn't 0. And that's how a massless particle can have energy. It must travel at the speed of light. So now let's think a bit about the theory of the Higgs field. The argument is that the Higgs field exists in all points in space throughout the universe. It's what is called a scalar field, and the idea is that the particles which have mass interact with that field, but particles without mass don't. Now, just as with our room, which had temperature, we would say that at any point in the room you would have a number on the temperature scale which would represent the point of the temperature at that point in the room. Well, the Higgs field is a little bit more complicated than that. It has, as it were, 2 dimensions. It has the field itself and then the potential energy associated with that field. And the shape, for mathematical reasons which is a bit complicated to go into, but to give you the idea of the principle of the thing, the shape looks a bit like this. It's actually a 3-dimensional shape, so that is a kind of circle, and if you can imagine it, it's like an inverted Mexican hat. Now, where is the state of lowest energy? Everything always wants to get to its lowest energy. The answer is at the bottom of this curve or the bottom of this curve. But since it's 3-dimensional, it's essentially anywhere on this circle. That is where the energy is at its lowest. And the theory is that massless particles occupy this lowest energy state. But if you oscillate about that point there, which of course you can do all the way round, it's like a kind of gutter. If you oscillate in that section there, that oscillation is what gives rise to mass. And it's the interaction of the particle with the field that causes that oscillation that gives the particle mass. Think about light for a moment. Light is governed by the formula that the speed of light is equal to the frequency times its wavelength. Or if you like, c divided by lambda equals f. So if we plot the frequency against 1 over lambda, we are going to get a straight line. And the gradient of that line will simply be c. Now, what happens if we multiply both this term and this term by h, Planck's constant? hf is what Einstein described as the energy of the photon. So this now becomes energy. H over lambda is the de Broglie equation, and that is momentum. So we now have exactly the same graph, but now it's energy against momentum. And the straight line shows that the velocity is c. And what this shows is that when the energy is zero, the momentum is zero. But for a massive particle, we showed in the videos on special relativity that the energy is the square root of c squared p squared plus m squared c to the fourth, where m is the mass of the particle, p is the momentum, c is the speed of light, and E is the energy. Now that will give rise to a graph that looks like this. Here we're plotting energy against momentum. And even when the momentum is zero, there is still some energy. And that energy is the rest mass energy. And you can see from this formula that if the mass is zero, then i.e. it's a photon, then E equals simply pc, the square root of p squared c squared. Whereas if it's a massive particle with no momentum, in other words it's stationary, then E is simply the square root of m squared c to the fourth, which of course is mc squared, which is this rest mass here. So conceptually, how does the Higgs field work? Well, let's consider a room. And I am walking across that room. And I can walk across it very easily. Nothing really impedes me. All is fine. Now let's suppose that we fill that room half full with water. I will now struggle to walk across that room. I will be significantly impeded as I try to walk across the room. There will be far greater resistance. By contrast, a little fish in that water will dart about very quickly without any problem. And this, conceptually, is what the Higgs field is all about. I represent a massive particle. I struggle to get through the Higgs field, and that's how I acquire mass. The fish is the photon. It doesn't have any problem zipping about in the Higgs field, and therefore it doesn't get any resistance. Now, we've seen in earlier videos that wherever you have a field, it is what they call mediated by a gauge boson. For example, when we said that two electrons interact, we used a Feynman diagram. Here's an electron coming in, here's an electron going out. The two electrons are essentially just coming together and then repelling. But what we said was that it actually repels because there is some communication between the two that is done by a gauge boson, in this case, a photon. The photon is responsible for the exchange of information between the two electrons to cause them to repel. And when you get a Higgs field, that is mediated by the Higgs boson. How then can you find a Higgs boson? You can't photograph it. You can't even directly detect it because you don't actually know what you're looking for. But a Higgs boson is predicted to have a hefty mass, and it will decay into other particles. And it's those particles that you're looking for. You're looking for interactions which happen which generate more of one type of particle than you were expecting, which will give you a hint that the Higgs boson has decayed into those particles. Theoretical physicists have narrowed the field down for the Higgs boson to have a mass somewhere between 100 and 500 GeV. The Higgs boson needs to be pretty massive in order to give mass to the heaviest of the elementary particles. By contrast, of course, a proton has a mass of approximately 1 GeV. So the Higgs boson is at least 100 times bigger than the mass of a proton. Now the question is, what does a Higgs boson decay into? And the answer is, well, it depends how big it is, or how massive it is, because it will decay into elementary particles which are broadly of the same mass that it is. So if, for example, the Higgs is only 100 GeV, then it's likely to decay into a bottom quark. If it's about here, it might decay into a bottom quark or a W boson. Here, it's probably just going to decay into a W boson. Here, it can decay into a W or a Z. And at the top range, you would expect it to decay into a W or a Z or a top quark. So depending on the mass, you will find that the decay products differ. Now, many experiments have already been done, and directly or indirectly, a huge range of this has already been ruled out to the what they call 95% confidence level. That means we're 95% confident that the Higgs boson isn't anywhere in this range or in this range. And that leaves a very narrow range of 115 to 127 GeV, which is the range where you're likely to get something like a bottom quark or a W boson. So in the Large Hadron Collider in CERN, what is happening is that two protons are being collided together at very, very, very close to the speed of light each, resulting in a cataclysmic kind of smashing together with all sorts of things being produced. And what the scientists are looking for is evidence of a Higgs boson. In other words, they're probably looking for slightly more bottom quarks or W bosons than they might expect. How does this manifest itself? Well, it's probably not as glamorous as you might think. The Higgs boson doesn't just appear and say, hello, here I am. What is typically likely to happen is that you're going to have some kind of graph with a distribution showing emitted particles. And that would be all sorts of different particles. And what you're looking for is some kind of blip on the side of the graph that suggests that there was slightly more than you were expecting. And that could be evidence of the existence of the Higgs boson, because this suggests that there are more decay particles than you were otherwise expected. However, it could be evidence of something completely different, which is why the experiment needs to be done in several places and at several different times to verify, in order to be able to give you the 95% confidence level that you need to be sure that you've found the Higgs boson that is responsible for giving mass to elementary particles.